Okay, in this video, we will derive the energy balance for a CSTR. So, as with every derivation that we do, let's start this derivation by drawing the system. So, we know that a CSTR is a tank reactor, so I'm going to draw a tank reactor. And you have to excuse my not so great drawing abilities. So I've drawn this tank. We have the tank has a stir. And maybe it's a liquid reaction and maybe it's filled about this far. We have stuff coming in here. So reactants and products. So if this is a reaction, the reaction being carried out here is A plus B over A. B goes to C over A. C plus D over A. D. Coming in, we might be flowing, for example, our reactants, FA naught, FB naught. These are coming in at some temperature, T naught. Coming out then, I might have, or I probably will have, unspent reactants, as well as products. And also this will be at some temperature T. And the concentrations of all of these species, as well as the temperature, are the same as that in the tank. So if I have a CSTR with heat exchange, then I start to think about a heat exchanger. So typically for a CSTR, we think about that as being a jacket. So I'm going to draw a jacket around this CSTR. So you can think about the jacket being some insulated material with some space, and the space will have some cooling fluid. So into here, we have a cooling fluid, so we flow in a cooling fluid, so I have M dot C, and this is coming in at a temperature TA1, so the subscript C stands for coolant, and the subscript A stands for ambient, and I apologize that those are different, but it's the way the book uses the notation. And then, I didn't save myself room, but basically this is going to come out here. I'm going to have the same flow rate coming out, so C doesn't react, so it just flows in and out. It might change temperature, so because of that, I'll say that the flow rate coming out is TA2. So we can draw, or we can write an energy balance on this system. So if we start from the general form of the balance, what that means is that, and we assume steady state, then we had 0 is equal to Q dot plus WS dot plus flows times enthalpies coming in minus flows times enthalpies coming out. So now the next step is to cancel terms. In the CSTR, the stir is doing work on the reactor fluid. So in the PFR case, or the tubular reactor case, we crossed this term out. In the CSTR, we actually have a piece of mechanical equipment. So the stir is agitating the contents there, and hence it's adding energy to the system. However, the amount of energy that it adds is usually very small compared to the heat of reaction. So we can usually assume that WS is equal to 0. It's usually a good assumption. There are some exceptions. If the fluid is viscous, then maybe the stir has to work really hard, and so the amount of energy that it's adding is not insignificant. In this class, the recommendation would be to, if you're given information about the power or the work or something like that the stir is adding, then you should include it in your energy balance. If not, just make the assumption that WS is equal to 0. And in fact, in this case, we are going to set Ws equal to 0. Okay, so now my heat terms. So there's two cases that I can think of for my heat terms. So if I go back to my system, one case is that the heat or the temperature varies in this cooling fluid. So it comes in at one temperature, maybe a cooler temperature, and then it basically flows all the way around the reactor, and then once it exits, it's at another temperature, probably a hotter temperature. So it exchanges enough heat with the reactor contents to change its temperature. In that case, we would write the heat transfer term using a log mean temperature difference. So log mean temperature difference. So that would look something like this. On the other hand, sometimes we can say that the coolant flow rate is very fast, and because of that, the temperature of the coolant doesn't change, or it doesn't change noticeably from the inlet to the outlet. In that case, we can make the assumption that the rate of heat transfer, Q, is constant over the heat transfer area. In that case, we can use the simpler expression for Q. We can say that Q is equal to UA TA minus T, or in this case, TA1 equals TA2 equals TA. So most of the time in this class, we're going to use this example. I can't even think of an example off the top of my head where we use the log mean temperature difference. So let's carry out the derivation using this term. Okay, so in that case, we've made the assumption that Ws goes to 0. We have an expression for Q dot. All now we have to do is fill in the terms for the F times H. So let's do that. So we would have 0 equals the Q term, UA TA minus T, where T is the temperature of the reactor fluid, plus the sum of the flow rates times the enthalpies of formation of the stuff coming in. So we said A and B were coming in. So we would say FA naught, the inlet flow rate, times HA naught, plus FB naught times HB naught. And then coming out, we have all of the different species, A, B, C, and D. And since the temperature has changed, they're going to be at a new enthalpy. So we can say FA HA minus FB HB minus FC HC minus FD HD. And that's the energy balance for this particular CSTR. So let's take this expression and simplify it. So what we're trying to do here is get to the point of having a system of two equations and two unknowns. One of the equations is going to be the mole balance, the other is going to be the energy balance, and the unknowns are going to be the conversion and that the reactor achieves, and also the temperature of the contents inside the reactor. So right now what we're going to do is simplify down this energy balance so that it becomes a solvable expression when coupled with the material balance. So the first thing to do is to recognize that we have just one reaction going on. So a lot of these terms, in fact, all of the flow rates coming out of the reactor can be related to each other using this value x. So let's go ahead and do that. So we can say FA equals FA naught 1 minus x. So here we're assuming that A is the limiting reactant, FB. So if we take all of these and we substitute them into here, then we get 0. So now I have included these I've included these expressions in terms of conversion into the energy balance. Now what I want to do is expand out terms so that I can group x's together. So that's what I'm going to do next. So I have 0 equals. Okay. So now I'm going to take this expression and I'm going to group like terms. Okay, so when I group like terms, basically what I'm doing is I'm taking everything that's multiplied by x and putting that into a single term. Notice what I have here, these enthalpies, these H's are heats of formation. So again, just like in the case of the tubular reactor, this heat of reaction term falls out. And so whenever I'm taking an energy balance on a chemical reactor, I want this energy or this heat of reaction term to fall out. If it doesn't happen, that probably means I've done something incorrectly along the way. So therefore, I can simplify the balance, the energy balance, the equation. So now I have this heat of reaction term here. So now we're getting to a formula that we're almost ready to solve. So we should know these inlet values. For example, if we know the inlet temperature, that means that we also know the inlet enthalpies, which means that we're getting down to an equation of with two unknowns, temperature and conversion. Before we do that, though, we have to make some substitutions. So, for example, these terms, HIO minus HI, such as we have here and here, those are sensible heat. So that's taking the heat of formation from whatever temperature it is, and when it enters to that inside the reactor. So those are equal to a heat capacity times a temperature difference. So if we include that, okay, so what we've done here is basically said that this is a sensible heat change, which can be equal to or set equal to a heat capacity times a temperature difference. In this case, the temperature difference is the inlet temperature minus the temperature of the reactor contents. So this, if we know the heat capacities, we can solve this equation. Let's solve for x. If we do so, this is what we get. The conversion is equal to the sensible heat change of A plus the sensible heat change of B plus the heat exchanger, the amount of heat removed from the heat exchanger, divided by the heat given off due to the reaction. So ultimately in this equation, we have two unknowns. One is the conversion, the other one is the temperature. We hence need two equations, so we can couple this with a mole balance. The mole balance is the same as in the isothermal case, except now we have our rate expression has terms in it that are sensitive to the temperature, including the concentrations and the rate constant. We can couple all of these things together or embed these different temperature-dependent terms into this mole balance. That will give us two equations, two unknowns. Usually we like to write the mole balance. When we solve for x, we'll denote it as xmb. In this energy balance case, we've denoted it as xeb. When we solve, both of those will be the same, but we just denote them with different subscripts so that we can distinguish them in our solution procedure. And in the next video, I'll show how to solve a CSTR with heat effects.